Today we are going to discuss the time period of a simple pendulum of very large length or infinite length. So we have Earth of mass capital M and radius r, and above it we have a simple pendulum having mass m and length L, which is quite large. If I displace the simple pendulum from the vertical by an angular displacement theta, since the length L is quite large, in this case the linear displacement x will also be quite large. Another thing that is to be kept in mind is the weight mg, whose one of the components give us the restoring torque, will not be acting vertically downwards, but it will be acting towards the center of the earth like this. In this direction it will be acting mg. Also, if we produce this line L like this, then this line will be making an angle which will be equal to theta and plus, let us say this angle is phi. This angle is phi. So theta plus phi, external angle, is equal to the sum of opposite internal angles. So these things we must keep in mind before solving this problem. Now the torque, the restoring torque, will be acting in this direction, and this component of the restoring torque will be mg sine theta plus phi. So we can write that the restoring torque, which is I alpha in magnitude, and there should be a minus sign because it is a restoring torque, and the magnitude of this restoring torque will be mg sine theta plus phi multiplied by the length L, and this should be equal to negative of moment of inertia of this small bob will be ml square about the point of suspension, and into angular acceleration alpha. Now one thing we have to keep in mind to satisfy the conditions of simple harmonic motion, that theta will be small and also phi will be small. So since theta and phi are small, we can write sine of theta plus phi to be approximately equal to theta plus phi. So m we can cancel here, one L will get cancelled. So we can write that g into theta plus phi will be equal to minus of L into angular acceleration, or the angular acceleration can be written as minus of g by L and into theta plus phi. Now the angular displacement that is important to us is theta. So the double differentiation of theta with respect to time is alpha. So we have to write a relation between alpha and theta only. That thing we have to keep in mind. So I am going to take theta common from here. So the angular acceleration alpha will be equal to minus g by L into theta and 1 plus phi upon theta. So let us say this is equation number 1. Another thing that we can write is x equal to L theta, and this will also be equal to r into phi. So using this as second equation and putting these values in 1, we can write the angular acceleration as minus of g by L, and theta I will write later on, and into 1 plus, in place of phi, from equation number 2, phi can be written as x upon r, and divided by theta can be written as x upon L, and into angular displacement theta. This x gets cancelled. So we have angular acceleration equal to minus g by L and 1 plus L by r. And then if I multiply by 1 by L, then we get angular acceleration as minus g into 1 by L plus 1 by r and into theta. So if I compare it with the equation of SHM, which is alpha equal to minus omega square theta for angular SHM, then omega comes out to be equal to under root g into 1 by L plus 1 by r. And so the time period, which is 2 pi by omega, so we can write the time period as 2 pi and under root of 1 upon g and into 1 by L plus 1 by r. And if I take L tending to infinity, then the term 1 by L will become 0. So this implies 1 by L will tend to 0. So the time period in the limiting case will be under root. G will be in the numerator and g into 1 by r. So r will go in the numerator and g will be left in the denominator. So this will be the final answer. So that is it. This is the time period of an infinitely long simple pendulum. I hope you get it. Thank you.